welcome to a video about magnetic field strength. For some reason again the iPad has blocked my terrific pictures. This one, hopefully as you'll see on the notes, is just a magnet with some barbells. I'm not really sure what's going on, but the iPad seems to have cracked it. Anyway, the magnitude of the magnetic field strength represented by B at radial distance r from the centre of a current carrying conductor is given by the rule magnetic field strength equals, that's the permeability of free space symbol, times by current divided by 2 pi r, and the permeability of free space divided by 2 pi is a constant. That's equal to 2.0 by 10 to the negative 7 Tesla meters per ampere. In stage 2 physics, you'll be expected to be able to solve problems involving the use of this rule. So, magnetic field strength, just a quick definition, is a measure of magnetic force acting on a moving charge or electric current. As we said, it's equivalent or equal to this rule here. The SI unit is Tesla, so T for Tesla, and the charge is measured in current, and the radial distance r is measured in meters. Sorry, I think I said the charge is measured in current. That was meant to be charge of the particle or object is measured in amperes or amps. And then the magnetic field constant, which is this permeability of free space over 2 pi, is measured in Tesla meters per amps. The permeability of free space is similar to the permittivity of free space, that E with a little zero, and it just impacts the magnitude and propagation of magnetic fields through free space. So we've got a straight copper wire, it carries 1.5 amps of current. What is the magnetic field strength 50 centimetres from the centre of this wire? Because we're doing everything, our units for R are in metres, 50 centimetres is 0.5 metres. We'll write our rule, which is magnetic field strength is equal to this little U permeability thing, times by I, which is the charge, divided by 2 pi, and then r, which is the radial distance from the centre of the current carrying conductor. So the permeability divided by 2 pi, that will be 2.0 by 10 to the negative 7, because that's a constant. Our I will be 1.5 amps and our R will be 0.5 meters. So this, if you pop it into a calculator, you might even just be able to look at this one, will be 6.00 by 10 to the negative 7 Teslas. So that's the strength of the magnetic field, 50 centimeters from the center of the wire, which is carrying the current. Another example question, you've got a transmission power line which carries a current of 500 amps. Calculate the radial distance from the wire at which the magnetic field strength is 22 microteslas. Micro is 10 to the negative 6, so we've got 10 to the negative 6 Tesla. So sometimes it can be handy to do your conversion straight away, just so you're not accidentally forgetting and then losing marks just for something as simple as that. But whatever works best for you. So we'll use our rule again. We'll use magnetic field strength B is equal to permeability times by I, and then over 2 pi r. In this we're looking for r, the radial distance, so all we'll have to do is rearrange our equation to get r is equal to permeability by I over 2 pi b. So R will be equal to, and then 2.00 by 10 to the negative 7, because that's our constant, the permeability divided by 2 pi. This time I is 500 amps, and we're dividing by B, which is 22 by 10 to the negative 6 Teslas, or 22 microteslas. If you pop all of that into a calculator, you'll get 4.55 meters. So the magnetic field strength is 22 microteslas at 4.55 meters away from this current carrying wire.